Well done. Okay, so last class we ended by talking about Dijkstra's algorithm, which you're going to explore more in the homework, but also in on Friday's class. So reminder, what you're trying to do is you're trying to minimize the total length, because that's what you're trying to do, right? You're trying to get the lightest path. So at every point you have the weight to, when a vertex enters the set of things you've seen, right, you have a candidate lightest weight, and from there you're basically spanning out to say, let me look at all the neighbors, let me add the weight so far to the weight of this edge, and I'm going to take the lightest weight to that. Okay? And that gives me the new lightest weight, it gives me a new vertex, and I sequentially add more vertices. Okay? That's the basic idea. That's essentially the whole algorithm. And then there's some bookkeeping details you have to worry about, like how do I do this reasonably efficiently. You're doing a lab where you're learning about queues, and then you're going to see more details when you look at the assignment statement. Somebody asked me at the end of class, would this problem be any different if we did this over essentially a two-dimensional plane? And the way we've set up the problem for you, in fact, that is how we're doing it. We're doing it over something called Manhattan distance. So the idea of Manhattan distance is you have some kind of grid, and you only look at traversals along the grid. Okay? That's different from Euclidean distance, where the distance from here to here is literally what you might call as the crow flies distance, right? But on the Manhattan grid, at least for now, you still have to go along the ground until somebody figures out how to make air taxis that go along Euclidean distance. So that's why it's called Manhattan distance. Okay? So it's like a bad name. It doesn't anticipate flying cars, essentially. Okay? So that's what Manhattan distance is, kind of grid distance. Yeah.
Is there a way to represent like paths inside graphs that you don't want to be like studded with nodes without?
Yeah, not really. Not really. I mean, this is just what happens when you're trying to map a terrain onto some data structure, right? Now, an interesting question is, what if you're trying to actually represent continuous space, like the surface of the planet, right? You're not actually going to make a graph that represents every single point on the planet. So there's actually a branch, and this is what I wanted to comment on, there's actually a branch of graph theory that basically, there's sort of multiple branches of graph theory, one of which talks about, how do you represent actual spatial graphs, right? So in a spatial graph, you have some physical limitations, but other than that, essentially every point is fair play, okay? And that's a point that's going to become relevant in about a minute. The other aspect of it is, if I know that my graph is embeddable on the plane, so my graph can be represented on a two-dimensional plane, then can I come up with better algorithms? Because it's also a very interesting special case. I mean, it's just a special case. It just so happens that's the one we happen to live on, right? So if you're looking at a transportation network or a road network, it doesn't apply to airplane networks, but transportation networks, road networks, city grids, and things like that, they actually are very much embeddable in the plane because they are on the plane. So that's a special graph algorithm subfield called planar graph algorithms. And you happen to work in a department, one of the world's experts on it works upstairs, Philip Klein. Okay, so Philip Klein actually teaches a graduate course on planar graph algorithms. So if that's something that really interests you and excites you, that's something to look forward to. Okay, good? Ready to move on? Okay, today I want to talk about a different graph algorithm, which is going to be a different homework for you. And again, we'll do more examples of this in class. So I'm not doing many examples. You'll do examples of this as well next class. Okay, you'll even get a paper handout, I hope, if Tim does what I was hoping he'll do. So, here's the question we're interested in. Okay? And in fact, before I even get to the question, I'm going to tell you about a question behind the question. In the year 2000, the National Academy of Engineering, so National Academy of Engineering is like the great engineers of America, right? All the living great engineers of America, did a survey saying, okay, what were the great engineering achievements of the past century? Right? What are the top engineering achievements of the past century? So what would you think of as the great engineering achievements of the 20th century? There's some pretty obvious ones, right? What are great achievements of the 20th century? Yeah, yes? Panama Canal. Oh, Panama Canal. I like that. Yeah.
I mean, it's straight. It's not like good. nuclear weapons.
Okay, so nuclear power you could say is great, and then nuclear weapons is the not so good side of great, right? Okay, great. Nuclear power certainly harnessing the power of the atom, as people use. That was a phrase people used to use 100 years ago. Not 100 years.
I was also going to say.
Okay, other examples? Great. Other examples? Yeah.
Space exploration.
So just rocketry in general as an engineering activity. Yeah.
Computers.
Computers. Yeah, the microchip, right? Microchip is an amazing thing. Yeah.
Airplanes.
Airplanes, right? Okay, good. All of these things. Yeah.
Like refrigerators and microwaves?
Refrigerators and refrigeration, right? Refrigeration suddenly changed the way people ate. It's literally, I mean, the fact that I can get a tomato in October is a statement about refrigeration, right? Or I can get an avocado or anything, right? Huge refrigerators. Some refrigerators have wheels and they drive across the country and they're called refrigerator trucks, but basically they're refrigerators on wheels. Yeah.
Accessible cars.
Oh yeah, accessible cars. Okay, so all of these are like great achievements of the 20th century, right? Cars again changed the landscape, made all sorts of good things happen, maybe also had some negative externalities, right? Okay, good. So what's interesting is this wasn't their top pick. None of these things was their top pick. And these are engineers, they obviously know about all of these things. They picked a much more interesting example. They said rural electrification. What? What does rural electrification even mean? Is that even English? What does rural electrification mean? What does it mean? Yeah.
Bringing electricity away from the cities.
Yeah, bring electricity to, is that same answer? It's to bring electricity all over the place. Why does it even matter? Why is it any kind of achievement? I mean, obviously it's like difficult, right? You have to string wires all across the country. But what consequence does that have? Yeah.
Connects everything.
It connects everything.
Oh, it changed how we do agriculture.
It changes how you do agriculture. It also creates marketplaces. If you think about the 1920s, 1930s, most of the world was pretty agrarian, right? Like agricultural based. So cities were not that big. In fact, if you look at countries like Brazil, about 80 to 90, I think about 90% of Brazil now lives within about 10 miles of an ocean. Right? But that's not how Brazil used to be. Basically, like everybody has been sucked away from the middle of Brazil to the fringes of Brazil. Australia, same way, right? There's nothing in the middle, everybody lives on the fringes. But that wasn't always the case. And people, even in the US, a lot of people lived in rural areas. But that meant that a marketplace couldn't be created if you couldn't use the rural people as part of your marketplace. So if you could say now they have electricity, now it made sense for them to be able to buy a fridge. Otherwise, what are they going to do? Turn a crank, right? So for things like refrigeration and microwaves, none of these things made sense. And so the marketplace was much smaller. And so sort of everything changed, like the entire way of life changed. You mentioned refrigeration, right? Refrigeration was phenomenal, but it wouldn't have been possible without rural electrification, right? In fact, it's kind of weird when you think about it. Right? There's pretty much one thing, with the exception of airplanes, which are not terrestrial, and they have their own issues, and even that's starting to change a little bit, but there's just one thing that really doesn't work on electricity. Cars. It's kind of ludicrous that cars carry a power plant in them. Just think about it. There's a power plant. There's, thousands of explosions, literally kaboom, kaboom, explosions happening every minute inside your automobile. Every time you turn it on, it's like an astoundingly crazy thing that they carry a power plant along, right? So you've lost the abstraction of consumers and producers. What rural electrification does is it creates a consistent API for everything. Right? It creates a standard API, and the API is the electron. It says, as long as you can consume electrons, you're good to go. Right? You don't have refrigerators that have a power plant. You don't take like kerosene and pour it into your refrigerator every morning and say, please refrigerator run for the day. Right? You can abstract away the consumption from the production. And you can now produce those electrons from lots of sources. You can use turbines, of course, you can use coal, you can use gas, you can use wind, you can use the sea, you can use all these sources now because you get a common abstraction. The API is the electron, right? And automobiles are the only things that don't have that API, so you have to have this other weird abstraction where you have to pour like dead dinosaurs into your car so that you can actually make it go a few miles, right? So it's kind of weird when you think about cars. So like electric cars are actually like the most obvious thing in the world because like why the heck do they have to carry a power plant along? Hey, can you imagine if every household had next to it a power plant? They're like, that's the only way it could get things done. That's what a car is. It's just a completely bizarre and broken idea. Okay, anyway, enough ranting about cars. There's actually like all sorts of things I can say about cars I don't want to get into. So, rural, yeah.
Well, I mean, I don't know.
No, I really don't want to argue about cars. No, okay, yeah. I can tell from the look on your face this is going to be way too interesting. So I have a job to do here, man. All right, so I want to transport you in time to about 1920s, okay? So rural electrification in the US happened, you know when it happened? When did the rurals get electrification?
Probably late 30s, early 40s.
Yeah, 20s, 30s. So it's part of Works Project Administration was a major force. But even before that, in the late 20s, people were starting to think about this. But the US wasn't the only country thinking about rural electrification. In the 20s, everybody was like, you know, the cities have like lamps at night. The streets, you can walk in the streets out holding a lamp of your own, right? You don't have to carry a power plant that's generating power. Something else, some abstraction gives you power and therefore gives you lights. Wouldn't it be nice if we could all have such things, okay? So specifically, I want to talk about one particular part of the world that was thinking quite hard about rural electrification, which is Moravia. What's Moravia? It's not a fake country, you know, like Moravia is like a real place. Where's Moravia? You know, Moravia. Yeah, it's somewhere out there. Yeah, it's now you'd say it's part of the Czech Republic. It's like a corner of the Czech Republic. Okay, so Moravia, the sort of state, the region of Moravia, was one of the many places thinking about rural electrification. So they charged engineers. They had electrical engineers. They said, "Hey, electrical engineers, go figure out how to do this electricity thing that you do." Okay? So engineers thought about this, and one particular person named Otkar Boruvka. Okay, Boruvka is particularly interesting because of the many engineers who think about it. Boruvka thought about it more deeply than anybody else. So here's what Boruvka said. Okay, so we need to create a grid, right? We need to connect all these places with, you know, wires. What is the characteristic we would like of an electrical grid? So we've been talking about things like, you know, lightest pads, right? We've been talking about reachability, connectedness, things like that. What are the characteristics you would want for an electrical grid? Yeah.
If one part of the grid goes down for some reason, you don't want the whole.
Fault tolerance. One part of the grid goes down, you don't want the whole grid to go down. Very interesting. What else would you like of a grid? What else would you like of a grid? Yes?
You want to like cover the most amount of space with the least amount of
Yeah, you want to cover the most amount of space, least amount of cost, right? Related to this Dijkstra thing, it's an optimization problem. Yeah. Somebody else had a hand up here.
It's weighted because you lose electricity for every like meter of wire.
Oh, you have to worry about weights because, yeah, in particular, wire has resistance and the resistance becomes an issue. Yeah.
Capacity,
Capacity. What about capacity?
the total amount of electrical energy you can transmit.
Yeah, so you have to think about capacity, carrying costs, yeah. Other things. Okay, so if we are trying to develop a grid network, what is a critical thing we would like? Like if you are a city here and you have an incoming line that provides electricity from, I don't know, like a hydroelectric plant up in Maine or something like that, you actually, there's a really important thing you like. You want network-wide resiliency. You also want every city to have some resiliency, right? Like you want these packets that happen to be called electrons to be able to come from multiple different places, right? You want redundancy, okay? Just like the internet has redundancy, you want your electrical network. You want all sorts of networks to have redundancy. Your road network has redundancy. You want your electrical network to have redundancy. But you know what? Not everybody has that luxury. So I grew up in India, and when I was growing up, it was routine for the electrical network to go down numerous hours a day. It would in particular go down like the hottest point of the day, which is when you most needed it. It'd be like, yeah, sorry, too many people want the electricity, no electricity for you now, right? It wasn't true for everyone. Like if you lived on the same street as a politician, like an important politician, it didn't go down for you magically, okay? I didn't. So the computer would go down periodically and, you know, life sucked, okay? So you got very used to like electricity. So I was very amazed when I came to the US and discovered like electricity is actually on all day long. Like, what strange magic is this? Like, when does it go off? It doesn't go off. No, surely you're joking. No, it doesn't go off. Right? But it turns out when it goes off, you're completely screwed. Nobody in America has any clue what to do when the electricity goes off. It's called like a blackout, and like people tweet about it. And it's like, if you grew up without the electricity going off all the time, you learn fault tolerance, right? So it has some advantages, I think. So anyway, the point is, when you are first rolling out a network, an electrical network, right? You can't afford, you have to make a choice. Is it more important to be redundant, like you want to make sure like, the second city gets redundant, like redundant networks, or do you want to make sure you connect everybody so that most people get some electricity at least some of the time? That's a choice, okay? So Boruvka said, look, we want to make sure that everybody gets at least some electricity. Yes, sometimes the network will go down. Someday when we have more money, we can build multiple routes, we can give them redundancy. But the more critical thing is make sure like everybody, everybody gets at least some electricity, and we want to make sure we can do this at the lowest cost. Okay? So if you want to make sure everybody gets electricity and there's no redundancy, that means there are no DAGs and there are no cycles, right? Because DAGs means redundancy and cycles means you're looping back around. You clearly can cut off one of the things in the cycle, right? So you want trees. So you want your network to be a tree. And you want it to cost as little as possible, and you want it to reach all of the places in the country, right? So what Boruvka did was he thought very hard and he said, you know what, this has nothing to do really with electricity. I can think about modeling this as a problem where there are nodes and there are edges. I mean, this was a very, very, very sophisticated idea for his time, right? I mean, it's just this engineer working like a small, tiny little part of the world that you don't even know where it is on the map, right? I mean, he did. Okay. People from Moravia know where it is. But the point is, it's not like a major intellectual center of the universe kind of thing. But he was thinking about this hard, and he said, okay, I'm going to abstract this out into a graph problem. Okay? So he said, I'm going to build Moravian spanning, meaning they reach all the nodes, trees, because we can't afford redundancy. It's more important we get everybody at least some electricity, and later on we can add more things. Okay? So you define this problem of Moravian spanning trees. Okay? So Boruvka defines this problem, and the problem sitting there, and somebody has to come up with a solution. And so in about 1930, another electrical engineer named Yarnik published a solution to this problem. Very elegant solution, except it turns out nobody really reads Czech math journals all that much. And so in the Western world, we call this Prim's algorithm, because, so this was 1930, Prim was 1957, but everyone calls this Prim's algorithm, but it's really Yarnik's algorithm because Yarnik figured out the solution first. It's the same solution. So here is the idea behind Prim's solution, okay? It's actually the one I first faked you out with in class last class. So what Prim's algorithm does is it basically says I have a current solution, okay? I have a current tree. I'm going to look at all of the edges that are adjacent to the nodes that are currently in the tree. I am simply going to pick the lightest edge. I'm going to add that to the tree and go on. Okay? With one caveat. Remember, I need to make sure that it is a tree. So when I'm about to add a candidate edge, I have to check whether doing so would create a cycle. Because if doing so would create a cycle, then clearly I have a redundancy. I skip that edge and I move on to the next edge. Okay? So you need a relatively efficient algorithm that I have not shown you, I have not talked about yet. We're going to do that next week. Okay? We need a relatively efficient algorithm for figuring out whether if I'm about to add an edge to an existing solution, right? So an existing, hopefully it's already a tree, it's still a tree. When I'm about to add an edge, will that make this, are those two endpoints already connected? Because if they're already connected, there was no point adding them because now I created a redundant edge. Does that make sense? Okay, now there's an easy way of checking this, right? What's the easy way of checking whether if I add an edge, I'm now going to get a cycle? Yeah.
Whether it's already in your solution, the node that it's connected.
I could check that the node's already in my solution. And yeah, so I simply check whether it's already in the solution, right? And in general, that's what reachability already does, right? So what I want is something more efficient than that, because I'd have to scan things and I have to look at things. We can think about what to do, what it means to make that more efficient, okay? So the bottom line is, before I add something, I need to make sure that adding that thing will not make redundancy. That adding that thing will maintain treeness. If it doesn't, then I want to discard that edge and go on to the next edge, right? Keep going on to the next lightest edge, till I get to an edge that will not create a loop, and that's the edge that I add, and then I'd repeat this, and I keep doing this basically till I run out of edges to add and I run out of vertices, right? Now, that doesn't guarantee me that I'm going to actually reach all of the vertices, because maybe the graph's not connected. I could have some vertices that are literally not reachable from my starting point, right? So that's a problem, right? What does the graph here correspond to? Well, the graph here, the nodes are going to be the cities in Moravia, the cities, towns, villages in Moravia, and the edges are going to be like, where is it feasible to build a connection, right? Like, why might it not be feasible to build a connection between two places? What?
Like mountains.
Yeah, mountains, lakes, like electricity through water apparently is a bit of a thing, right? So it's got some issues, right? Wolves, etc., right? Okay, and your cost function is basically like, how expensive is it to build this, right? Like, maybe mountains aren't so bad, but maybe your wolf cost is like infinitely high or something like that, right? So you got to worry about those things. So that's your cost, right? So you're basically, you go to your surveyors, you go to your geo surveyors, you get a map and you basically say, okay, these are the routes along which we can feasibly build them. This is what it would cost. It's some cost in terms of like the distance, the topology, and so on. Topography, I should say. Okay? Make sense? That's our graph. And if there's some village that for some reason is simply not reachable, it's like, I don't know, it's in a bowl surrounded by mountains, or I don't know, it's like, you know, it's an island that's surrounded by water, then, well, you can't reach that. So you're not going to span that. You can only span the reachable ones. Okay? So far, so good? Okay, so that's the algorithm, and notice that what that algorithm requires is that at every step you have to keep track of this, there's this graph and you're building out and you have to check which vertex is the next vertex, and you're constantly, like every time you add an edge, you get so many more adjacent vertices to look at, right? Because you start with one vertex, it's got a bunch of adjacent things. Now you add a second one, and now it's got a bunch of adjacent things, but all the original adjacent things are still in play. And then you add another one, and now all of its and all of the second ones and all of the third one's adjacent vertices are all in play. And you're constantly having to keep track of this priority list, right? Like, which is the lightest of all of these. And if you make a mistake, you screw up. You don't get the proper spanning tree, right? You don't get the spanning tree that has the least weight, right? This is easy for computers to do. It's not so easy for humans to do. Like, who cares? Why do we care about humans? Okay, I hope you have an answer to that question in general when you're going to computer science, okay? You are aware that there are humans who will use your systems, yes? And humans are not like completely irrational agents, and they're not infallible, and etc., etc. This is all not news to you, I hope. Okay, let it not be news to you from this moment forward, okay? So, look at the year I'm talking about. I'm talking about years like 1930 and 1957. So people actually had to run these algorithms by hand. And when you run these algorithms by hand over a large graph, right, hundreds of nodes, it's really kind of painful to have to do this by hand. So, can we do better? So here's an underexplored, perhaps for good reasons, underexplored area of computer science, algorithms that have to be run by human beings. Okay? Like, what is a good insorting algorithm if a human being is going to run this as opposed to a computer is going to run this? It turns out maybe it's not exactly the same sorting algorithm if a computer is going to run it, right? Because we care about auxiliary data structures, we care about bookkeeping, and those are different things depending on who's going to be doing the running. Okay? So I think it's not coincidental that around this era, well, actually slightly earlier, but all these people were writing in different places and different journals, and nobody knew about each other, and Google didn't exist and stuff like that. There was a very different algorithm that was created, and this was created by a person named Kruskal. And so Kruskal's algorithm is beautiful. It's incredibly elegantly simple. Okay. By the way, you're going to implement both of these for homework. Okay. Not only are you going to implement them, you're going to like test them against each other. Right? Because one of them, either one of them is correct. Hopefully you'll get both of them right. But you know, it's a useful thing you can do. Implement it twice and run them against each other and see whether they produce the same answers. Same answers? Will they always produce the same answers? Why not? Like one of them would be buggy, right? That's if they don't produce the same answer, clearly one of them is wrong. Clearly? If they don't produce the same answers, clearly one of them is wrong. Agree? How many of you agree? How many of you disagree? Why do you disagree? It seems pretty obvious. Can you all yell out a word?
Both.
Say it louder.
Oracle.
Oracle! Oracle, that's the whole point of oracles, right? You could have a relation, not a function. A given input could map to several different legal outputs. Can you have different minimal trees? Could you construct a graph with different minimal trees? Could you really? Talk to your neighbors, construct a graph with different minimal trees. Go.
Oh my god, I could not figure out what those actually. Well, if you okay, this one was
Okay, 5, 4, 3, 2, 1. Anyone, do you have a graph? You have a graph? Who has a graph? Somebody have a graph? You have a graph? You have a graph? You have a graph? Go, give me a graph.
A triangle.
Okay, hold on. A triangle.
Where the edges are undirected and all have weight 1.
All have weight 1. Okay, so somebody give me one minimal tree inside this triangle. Yeah.
The top left and the top right, both these.
Top left and top right.
So like top to bottom right.
Uh-huh.
And top to bottom left.
Top to bottom left. Okay, somebody give me a different tree in this graph. Yeah.
Kind of like an L with
So just tell me where.
top to left and then left to right.
Okay. And of course, there's another one there, right? Okay. So they're all weight 2, they all span, and they are different trees. Okay. So this is one of those problems. By the way, same thing is also true of Dijkstra's algorithm, right? Because anytime you have weights that are similar enough, you're going to get multiple possible solutions. Pretty much all graph algorithms have this property, that there's not usually a canonical answer. There are many answers because you're trying to solve an optimization question. Optimization question is where you express a problem in terms of finding the maximum or minimum of something. Give me the best, or not usually worst. You don't usually want the worst, but best can be sometimes the smallest number, best can be like the biggest number, right? So these are called optimization problems. And when you have optimization problems, it's quite standard to have multiple solutions to an optimization problem. And so testing that you got an optimization problem right is a little subtle. You usually want to test a characteristic of the solution rather than the exact solution. Let me repeat that. You want to test characteristics of the solution rather than the exact solution. Okay? And that's what you've already been doing in your Oracle homeworks. Now we're going to push you to do that a little more. Okay? Make sense? Good? All good? Okay. Okay. So now, let me tell you Kruskal's solution, because Kruskal's solution is really elegant. So Kruskal basically says, look, the problem is, I don't know if he actually said this, but you know, he might as well have. So Kruskal basically says, look, the problem is you're all obsessed with vertices, right? All of you graph people are obsessed with vertices. What actually matters is edges. Here's what I'm going to do. We're going to take all of the edges in the graph. You remember we talked about the representation of graphs as really being a list of edges and the vertices sort of came along for the ride? Okay, that's the representation we're going to use. I mean, you can use any representation you want, but we're going to think of that as our focal representation. So what he says is, take all of the edges and sort the edges in ascending order of weight. Okay? Easy, right? Sort the edges in ascending order of weight. Great. Now, let's just for the moment pretend, this is not a without loss of generality thing, but let's just pretend that all the edges are of different weights, okay? Just to make it a little visually simpler in our heads, okay? All the edges are different weight. Now, think about the lightest edge in the graph. Can we afford, and also this one for simplification, let's assume we're only talking about a graph where all the elements are connected to all the other elements, so we don't have to worry about like weird disconnected things, okay? So, all the elements are connected and all the edges are of different weights. So take the lightest weight edge in the graph. Can it not be part of the solution? The lightest weight edge in the graph. So we essentially what happens is we have a situation like this, right? I've got a graph, okay? I've got a bunch of vertices, I've got a bunch of edges, okay? And let's say this is the lightest weight edge in the graph. Ultimately, we are going to have to reach this node and we're going to have to reach this node. There's no choice, okay? If we had a solution that didn't include this edge, then, so let's say it included this edge over here and this edge, so it included these other four edges, right? I could simply take any of these edges, right? Like, well, any of the edges that are instant here. Let's say I just dropped that edge and included this edge, right? I have strictly improved my solution. Because I'm still just as connected as I was before. I still have a tree, but I got something that's strictly lighter, right? So that tells you that the lightest weight edge must be part of the solution. So we'll start with that as part of our solution. That's our first edge in the solution. Because his point is basically, our goal is not to add vertices, our goal is really to add edges. So why don't we shift our perspective and think in terms of edges rather than thinking always in terms of vertices, right? It's a really critical shift, it's a beautiful shift in perspective, okay? So we'll add the lightest weight edge. Now remove that from the list, okay? Repeat. We take the next lightest weight edge. Well, should that be part of the solution? Same argument, right? If that's not part of the solution, ultimately we're going to create something spanning. Well, we can just remove something else and put that in, so we should include that. Next lightest weight edge, okay? What is the only reason to not add an edge to the solution? A lightest edge. What is the only reason to not add a next lightest available edge?
It causes a redundancy.
It causes a redundancy. We no longer have a tree. Right? That's the only reason. So we still need this connectedness check, right? We still need to make sure that in the process of adding it, we do not create a cycle. That problem is never going to go away. That problem is fundamental to the idea that we are trying to construct trees. Okay? So what you do is you simply iterate lightest edge by lightest edge, and now we can actually generalize the problem away from assuming that all the edge weights are unique, because this works in general. We just take the edge weights, sort them, right? If we happen to have two different edges that are both the same lightest weight, well, we probably want both of them, right? Like, why would we not want one of them and want the other one? We want all of them. So we sort the edges by weight, we go through edge by edge, and for each edge, if it doesn't create a cycle, we add it. If it does create a cycle, we skip it, because we've already connected those two nodes, right? And adding that edge is only going to make a cycle and probably be heavier than what we already have, so we don't include it. Okay? So I haven't really given you a proof, obviously. The point is you can turn this into a proof. You basically do an inductive proof. You need a slightly stronger inductive invariant about, about the presence of cycles and why you can skip these. And then once you make an assumption about connectedness, you assume like the lightest so far, you can show that this actually does work. Yeah?
How often do greedy algorithms work?
I don't know what that is. Okay, so the point is that this algorithm is going to work. It's basically, here's the really interesting thing about this algorithm. Really interesting thing about this algorithm is it's far easier to use on paper. Because all you do is you do a one-time static sorting of all of the edges. Right? So essentially you go and you write down, on your notepad, you write down all of the edges in sorted order. There's no dynamic data structure to really keep track of. Because you look at the first edge, you add it to your solution, you scratch it out. You look at the next edge, you add it to your solution, you scratch it out. You look at the next edge, say, oh, this is going to create a cycle. Skip it, move on. Next edge, add it. Next edge, skip it, add it, skip it, skip it, skip it. I'm run out of edges, I'm done. And even before that, you can probably tell if you're done. Right? So it's a beautiful algorithm for a human being to run. This algorithm, like the other one, you'll see when you implement these, right? The other one's like kind of painful for a human being to have to keep track of like all these incident edges and they keep changing and whatnot. Kruskal's algorithm works beautifully when you just have to keep track of a sorted list of edges and you just walk through on a piece of paper and scratch them out. Make sense? Yes?
So say there are like two nodes that aren't connected to the original graph, but they're connected with each other, and electricity is provided here. Wouldn't that
Okay, so one thing that's important in this particular model is we have not separated consumers from producers of electricity. Everybody is assumed to be indiscriminate. Every node is just a node in the graph. Okay? So we can devise a more complicated model where we actually distinguish between producers and consumers. One of the nice things about electricity is actually it sort of flows both ways pretty evenly. Right? Like it doesn't really care. Right? So you're right. If you really go back to the original problem context, you do have to worry a little bit about a power plant is not the same as other things, right? And also, as you said, there's actually loss as you go along the wire. So being adjacent to the power plant is not the same as coming back to an adjacent node through a longer hop because you have to worry about decay and stuff like that, okay? Those are all very interesting modifications of this problem. The solution I'm presenting doesn't take those modifications into account, and it would actually be slightly interesting to come up with work out those modifications. Yes?
Would you consider, like, if you had a high voltage network connecting to a more local network, would you consider those two separate graphs, or would you consider them like?
I would think of those as actually two separate graphs because their characteristics are quite different, and then you'd have to figure out like what happens at the bridging point. This is not unrelated, by the way, to what actually happens on the internet. Right? Because the internet picture that you've all been taught is like, oh, there's all these nodes and they're all talking to each other and anything can reach anything else on the internet. It's a complete lie. Okay? The internet is actually broken down in a very hierarchical way. At a high level, for example, there are what are called administrative domains. Right? And each administrative domain is actually its own sort of closed network, and administrative domains have to talk to one another across like special protocols. So for instance, if you are sitting inside Google and you're sitting inside Brown, so you talk to Brown, right? You type www.google.com inside the Brown network, there's actually many weird things that are happening because Brown is probably, I haven't checked lately, but Brown's probably connected to, I don't know, like Verizon or something like that. Like that's probably our network provider. So the Brown domain has to talk to the Verizon domain, and then it goes over the Verizon backbone, and then the Verizon backbone has to talk to the Google domain. And the way that happens is that these high-level administrative domains have what are called peering relationships. They establish each other as peers, so they basically cooperate with each other, and they say, I agree to communicate with you, you agree to communicate with me, and there's also sometimes some money exchange involved, right? Because the internet doesn't actually run for free, right? So there are peering relationships, and there's agreements about like up and down, bandwidths and so on. And so it has to go and actually form a peering, and it's actually across the peering that the network communication happens. You don't actually talk to Google in any meaningful sense. You talk to something at Brown talks to something at Verizon talks to something else at Verizon, something goes to an interchange, what is known as a network interchange point. At the network interchange point, it talks to Google, and then it goes inside Google and gets routed. And astoundingly enough, all of this happens in like a hundredth of a second. Right, like that's the engineering behind that is simply mind-boggling. I'm actually leaving. The reason I'm not going to be in town on Friday is I'm going right now, like literally after class. I'm heading down to New York City to attend a NSF visioning event on the future of programmable networks. That's something we're actually very interested in at Brown. Rodrigo, Theo, Tim Nelson, and I have all done. Well, I think interesting work, but you may not agree. But anyway, we've done work, that much is undeniable, on how to program networks. So it turns out one of the big revolutions in networking about 10 years ago was how do we make it so that network devices are programmable by programmers rather than like Cisco provides you some functionality, you take it or you leave it. Until then, it used to be that the big network providers, Cisco, Juniper, whatnot, would give you a box and say, that's what you get. We'll give you these 17 features. If you want the 18th feature, you pay for the extra thing, you pay for a more expensive thing, etc. Right? And this was seriously hurting innovation, and a whole trend came along of what's called software-defined networking that said, how can we bring all the revolutions we have in software to also bear on the network so we can create new protocols, we can create new communication methods, because people have been inventing these and didn't have a way of getting them out into the world. And that's what software-defined networking is. And so that's turned into a general trend of programmable networks. So if you're interested in that topic, you're in a great department for that. We have at least 4 people in this department who'd be happy to talk to you and are actually actively working on it. Theo maybe being the most active person in the field right now. So, and Theo Benson's down there. Okay, so that's how the network actually works. So when you ask about high voltage, low voltage, it's like actually the internet is also kind of like that. Not high and low voltage, but it's actually a very complicated thing through these peering relationships. And there's something called BGP, which is the Border Gateway Protocol, which is how you use these peers to communicate with each other. And it's like, it's terrifying. The BGP is an extremely insecure protocol, and everything on the internet actually works kind of on trust. Did you just hear what I said? The only reason we're able to communicate on the internet is because of trust. And network engineers literally run around all day long patching mistakes in BGP configurations. Occasionally people publish broken BGP configurations. So for a certain period of time, I think it was YouTube, all of YouTube got directed to a random website in Pakistan because somebody at the top level domain in Pakistan published a bad BGP routing thing, and like everyone's like, oh, okay, well, we trust each other, right? So peering. So yeah, I guess that's where, and like all of YouTube, I think 15 minutes YouTube was down because it was all going to some random machine in Pakistan. And they're like, nah, bring it back, bring it back, bring it back. Like, this is literally the day-to-day of the internet, right? People almost die so your packets may live. So, you know, use the network responsibly. Okay, so, enough ranting about that. So here's the thing. There's a very interesting property going on in both of these algorithms and also in Dijkstra's algorithm. They have this property that we simply take the lightest next available choice, right? And it gives us a correct solution. That's called a greedy algorithm. A greedy algorithm means you can simply take the next available choice, the lightest available choice. The local lightweightness will give you a globally light solution. That seems pretty obvious, right? Like locally light solutions will give you a globally light solution. I encourage you to think of challenging yourself to come up with a situation where that's not going to be the case. And since networks and stuff are complicated, let me give you a very simple example. Think about making change, okay? Like making change, right? If I give you, in the U.S. currency system, if I give you, 10 cents and I ask you for change on 10 cents, what would you give me back? You give me one 10-cent coin. What about 9 cents? I say I want the minimal number of coins for 9 cents. Give me 5, whatever the 5 was, a nickel, right? A nickel and 4 cents, right? 4 pennies, whatever, okay? Okay, is that the best we can do? Can we do better than that? Here's a question. In the US currency system of coins, is it the case that if I greedily, right, this is what essentially like a machine would do, right? They'd say, okay, I'm going to give you the highest denomination available, right, till that denomination no longer applies, and then I'm going to take the next highest denomination. I'm going to keep taking the next highest denomination till I run out of coins, till I give you the change, right? That's what it would mean to be a greedy algorithm for giving you change, okay? In the US currency, if you applied the greedy algorithm, will you always get the least number of coins? Now, of course, we make this, it's like, well, coins actually have a weight, and maybe in terms of weight, maybe it's not the lightest in that sense. Let's just say we care about the least number of coins, okay? So we care about least number of coins. In the US currency system, will the greedy algorithm always give you the least number of coins? And then, so first, convince yourself one way or another. If you think it's false, you have to give me a counterexample. If you think it's true, then my next question is going to be, can you devise a currency system where that's not true? It's a fun little exercise, go think about it. But not now, because I'm not done here. Okay? So, this is Kruskal's algorithm. There's just one problem with both of these algorithms. They have this very centralized nature. You have to keep a global list of the current tree that we're forming, the current list of all the nodes that we've added, like what are the neighbors. They're really bad for parallel computers, right? Because they're very, very sequential algorithms. And so in 1965, a guy named Solin came up with a better parallel algorithm. What Solin basically said is, look, turns out there's no reason we should run this starting from only one node. In Dijkstra's case, it made sense to start it from only one node because we're saying from this source, what is the lightest path to something else? But if we just care about spanning the whole graph, why pick a particular starting node? Why not start with a graph? We start forming a tree from every single node that's available, right? So initially, every node tries to find its nearest neighbor. And then in the next stage, half of those nodes, are now out of circulation. The other half the nodes try to peer. Then the next stage, the other half the nodes try to peer, right? Basically what you get is you get a logarithmically sized tree because at every stage, half of the nodes are still participating in trying to form peers, right? And the only thing they can't do is they can't add an edge that would form a circle, right? So that's called Solin's algorithm, and it's madness to try to do this by hand. Okay? It's even pretty hard to do this by computer. It only made sense in an era when you had parallel computers available. Okay? Make sense? So that's why it showed up only in 1965. It's just a small twist in the story. It turned out Baruch had actually discovered that algorithm in 1924. He basically not only invented the question, he even came up with an algorithm. The problem is his algorithm was so complicated nobody could run it by hand, and so what Yarnik actually did was not invent the first solution, he invented the second solution, but the first solution that a mortal could actually run because Baruch was actually thinking about a great parallel universe. That's freaking amazing. It doesn't happen very often that somebody invents a problem and then figures out the most sophisticated solution from it up front, done. Right? This is like the ultimate mic drop in graph theory history that I know of. So it's actually, of course, in textbooks it's not called that. It's called the minimum spanning tree. But I think it's good to give Baruch a little credit. So, Moravian spanning tree is a good name too. And it's still the MST. So, okay? So that's the history of the MST algorithm. You're going to explore it more in your implementation. Now there was a question, when does the greedy algorithm work? Turns out there's a very interesting math answer to this question. There is a collection of algebraic structures called greedoids that basically characterize when the greedy algorithm works. And there's a theory of math called matroid theory. And matroid theory is basically a matroid is a sufficient condition for the greedy algorithm to work. And so there's a very clever algebraic structure that you can show things like Dijkstra's algorithm and minimum spanning tree and so on, and certain kinds of coin collections. I'm not saying whether the US is one of those, right? But certain coin collections actually fit the class of matroids, and you can use that to show that anything that's a matroid actually satisfies the greedy will actually give you the optimal solution on the greedy algorithm. And so when you get a new problem, if you know matroid theory, when you get a new problem, you simply prove that something is a matroid and boom, you're done. That may or may not be easier than actually constructing a greedy algorithm for the problem, but it does help you figure out, if you can't show that it's a matroid, then you probably shouldn't waste a lot of time coming up with a greedy algorithm. But if you can show it's a greedy algorithm, you're actually done. You can show it's a matroid. So sometimes really high-powered math can come in really handy. Okay? End of class. See you, I'll see you on Monday. But come to class on Friday. You're going to wish you did the homework.